everyone, this is Sir Marvin. So today for statics of rigid bodies, we're going to discuss the first lesson, which is the introduction to engineering mechanics. So for this lesson, we will have the following intended learning outcomes. So students must be able to, first one is to identify the principles of engineering mechanics. The second one is to enumerate axioms of mechanics. The third one is to recite Newton's laws of motion. The fourth one is to convert units, and the last one will be to identify different kinds of force systems. So as introduction to engineering mechanics, let us first define what engineering is. So engineering is the application of the mathematical and physical sciences, that is physics, chemistry, and biology, to the design and manufacture of items that benefit humanity. So everything that we see or use to make our lives more convenient or easier are actually products of engineering. So the buildings that we see, the cars or vehicles that we see on the road, even the simplest machines that we use on our daily lives are actually products of engineering. Now, let us define what mechanics is. So mechanics is the branch of physics that considers the action of forces on bodies or fluids that are at rest or in motion. Okay, so if we combine engineering and mechanics, so that will be engineering mechanics, and it is defined as the branch of engineering that applies the principles of mechanics to mechanical design. That is any design that must take into account the effect of forces. So in engineering mechanics, all the topics that we're going to discuss, we're going to take into consideration the effect of forces on rigid bodies. So let's define now what rigid body is. So rigid body is defined as a definite amount of matter, the parts of which are fixed in position relative to each other. So all of the bodies that we're going to discuss here in statics of rigid bodies, we will assume them as rigid. But in reality, there's no really such thing as rigid. Because if you're going to apply a specific force to a certain body, that body will experience deformation. So, meaning to say it's not really rigid. Okay, but the thing is, the deformation experienced by that body will just be too small, okay, compared to the size of the actual body. So, it will just be negligible. That's why we assumed it as rigid. Okay, so now let's talk about force. So force is defined as that of which changes or tends to change the state of motion of a body. If a force F acts on a particle of mass m, Newton's second law states that F is equal to ma, where m is mass and a is acceleration. Okay, so we can also use the formula F is equal to mg, where g is acceleration due to gravity, equal to 9.81 meter per second squared for metric system. So the units that we're going to use for force for metric system or SI system. So since F is equal to mg, so the unit for mass for metric system is kilogram, and the unit for gravity due to acceleration is meter per second squared. So kilogram times meter per second squared is actually equal to Newton. Now, for English system, the unit that we're going to use is lag times feet per second squared, which is actually equivalent to pound. There are two branches of engineering mechanics. So the first one is statics. So in statics, we consider the effects and distribution of forces on rigid bodies which are and remain at rest. So the second one is dynamics. In dynamics, we consider the motion of rigid bodies caused by the forces acting upon them. So the keyword here is in statics, the bodies to consider are at rest, while in dynamics, they are in motion. So now let's define what force system is. So force system is any arrangement where two or more forces act on a body or on a group of related bodies. Okay, so force system is always composed of two or more forces. So if there is a body or body subjected to two or more forces, that is actually a force system. So these are examples of force systems. Okay, so as you can see in your screen, and these are examples of force systems wherein a body is subjected to forces. So it's also the same here. This is the body and it is subjected by these forces. So the same with this body. This is subjected to these forces. Okay, so these are all examples of force systems. So there are different kinds of force system. So the first one is according to the plane it lies. So that is coplanar and non-coplanar. For coplanar, this force system lies in one plane. Otherwise, they are non-coplanar. So for coplanar force system, this force system only lies on a two dimension. Okay, let's say it's on y and x axis. Okay, while non-coplanar force systems, this force system acts on a three-dimensional plane. So this is an these are the examples of coplanar force systems wherein the forces, okay, or the force system itself only lies on x and y axis. Okay, this is just in two-dimensional. Okay, so the next example here, okay, this is actually in three-dimensional. Okay, so there are three axes here: the axis, the x-axis, and the z-axis. So this is in 3D. So this is non-coplanar. So the second classification is according to the line of action. So the first type under this classification is the concurrent force system. So concurrent force system, the lines of action of forces pass through a common point. So all of the forces here in concurrent force system meet at one point. Okay, that's why it's called concurrent. Okay, now for parallel force system, the lines of action of forces are parallel. So all of the forces involved in parallel force systems are all parallel with one another. Okay, so the third one is the non-concurrent force system. So the lines of action of forces are neither parallel nor intersect in a common point. So all of the force systems that are not concurrent force system nor parallel force system is non-concurrent force system. So this is an example of concurrent force system. So as you can see here, the forces here actually, if we're going to zoom this figure, no, so they won't really meet at a common point, right? But if you're going to extend the line of action of these forces, they will meet at a specific point. So that's why it's concurrent. It's still concurrent force system. Now for the second example, no, so this is an example of parallel force system. So as you can see, the forces here are all parallel, right? So the third example is actually a non-concurrent force system. So as you can see here, even if you extend the line of action of these forces, you can see that they will not all meet at a common point. So meaning to say, this is a non-concurrent force system. And this is also not a parallel force system, right? So this is really non-concurrent force system. Now, let's talk about the Newton's law of motion. So, we are familiar already with this laws of motion of Newton, right? So, let's uh, recite this, no? So, the first Newton's law of motion is the law of inertia. So, it states that a body at rest will remain at rest unless acted on by a force. Okay, the second one is the law of acceleration. It states that a body acted on a force or on by a force will accelerate in the direction of the force. And the last one is the law of action and reaction, which states that in every action, there is an equal and opposite reaction. So let's talk about now the axioms of mechanics. So these are the principles that we're going to use and apply here in mechanics. Okay, so the first axiom is the parallelogram law. So the resultant of two forces is the diagonal of the parallelogram formed on the vectors of these forces. So for parallelogram law, let's say you have two forces. So let's say this is the first force and this is the second force. So if we're going to offset, let's say this force, if you're going to offset it this way, so this will be the offset of that force. Also, Same here with this force. If we're going to offset this force, okay, so this will be the offset of that force. Okay, so as you can see here, there is a parallelogram law. I mean parallelogram form. Okay, so the diagonal of the parallelogram form will be the resultant. Okay, so this is an important principle that we're going to use no for the succeeding topics. Okay, so the second axiom is two forces are in equilibrium only when equal in magnitude, opposite in direction, and collinear in action. So if we have two forces, we can only say that they are in equilibrium if they satisfy all the conditions mentioned. So the first one, they should be equal in magnitude. So for the illustration here, okay, so if we have two forces here, so this force, the magnitude of this force should be equal to the magnitude of the other force, okay, to say that it is in equilibrium. Also, it should also satisfy that uh, the forces should be opposite in direction. So if this force is directed towards this direction, okay, so the other force should be directed oppositely. So it should be directed this way. Okay, and then the third condition, it should be collinear in action. So for these forces, okay, they should be collinear. So as we can see, they are actually collinear. So they have the same line of action, right? So since these forces, okay, satisfy these three conditions, okay, so we can say that these two forces are in equilibrium. So the third axiom is a set of forces in equilibrium may be added to any system of forces without changing the effect of the original system. So if you have a force system and you add another system to that system, okay, wherein the system that you add is in equilibrium, so the original system will remain unchanged. Okay, so because a system in equilibrium actually has a resultant of zero. Okay, so if you add that to a system, that system will just remain unchanged. Okay, so that's the third axiom. So the fourth one is action and reaction forces are equal but oppositely directed. So if you apply an action force, okay, so to a body, okay, so the body will react. So the reaction forces uh, that will act upon that body will be equal but oppositely directed. So here, as you can see here, let's say you apply an action force, okay, to this wall. So this wall will react, and then the reaction that will act upon the body should be equal to that action, okay, to that action force, but oppositely directed. So let's talk about now scalar and vector quantities. So scalars are quantities which possess magnitude only and can be added arithmetically, while vectors are quantities which possess both magnitude and direction and can be combined geometrically. So let's take this as an example. So let's say we have here a 30 Newton force and a 100 Newton force. So if we're going to treat them as scalars, if we sum them up, okay, so we can say that it's just 30 Newton plus 100 Newton, which will be equal to 130 Newton. But if we're going to treat them as vectors, okay, so we're going to take into consideration their direction. Okay, so let's say 30 Newton is directed towards the left. Okay, and 100 Newton is directed towards the right. Okay, so since the force that is directed to the right is larger than the force directed to the left, we can say that the force directed to the right will govern. Okay, so if we sum these forces up, okay, taking into consideration their direction, it will be 70 Newton, right? And it will be directed to the right since the larger force is directed to the right, so it will govern. Okay, so this will be the sum, okay, of these forces if we treat them as vectors. So we took into consideration their direction. So that's how you add vectors, no? Yun. Anyway, so now let's proceed to dimensional checks. So this is actually important. Okay, because all throughout this course, we're going to deal with dimensions or units. Okay, so we have to be consistent with the dimensions or units that we use in the formulas that we're going to use. Okay, so let's consider this. Okay, so we have here a formula, v squared is equal to vo squared plus 2as. Okay, so this is a familiar formula to you, right? So you see this often in your physics, right? So this is a formula. Okay, so here in dimensional checks, okay, so this is important that the dimension or the units at the left side of your equation, it should be equal to the dimensions or units at the right side of the equation. Okay, so let's check the dimension for this formula. So for v, okay, so we know that v is velocity, right? And let's say the unit that we use here is meter per second. Okay, let's say meter per second. So um, the unit here, therefore, in the left side will be meter per second quantity squared. So that will be meter squared over second squared. So the dimension at the right side of the equation should be the same. Okay, so it should also be meter per second quantity squared. Okay, so as we can see here, so BO or initial velocity is actually meter per second as well. So that will be quantity squared plus 2. So 2 is actually constant. And then A is acceleration. So acceleration is meter per second squared, right? Okay, and the unit for S is actually distance. So that is in meter. So if we're going to simplify this, so this will be multiplied here. So meter per second squared times m. Okay, so that will be meter times meter. So that will be meter squared over second squared, which is also the same with this. If we simplify this, this will be meter squared per second squared, right? So we can add this two dimensions. Okay, it will be meter per second quantity squared. So what happened here is the dimension at the right side of the equation will be equal to the dimension at the right. Okay, so that is important that you're consistent with the dimensions or units. Okay. So now let's talk about conversion of units. I know some of you have already learned this in your previous courses, but we have to recall this since this will be important to this course. Okay, you have to be knowledgeable in converting one unit to another because we're going to deal with units here in statics of rigid bodies. So as you can see in the screen, these are some of the most frequently used units here in statics of rigid bodies. So we have here tables for conversion factors for length, for weight or mass, and for force. Okay, so for the first table here, so this is a conversion of units from English system to another English system unit. So the second table is from metric system to metric system, and the third one is uh, uh, from English system to metric system and vice versa. Okay, so for the first table, okay, you have to be familiar with these conversion factors for length. You should memorize that 1 foot is equal to 12 inches, 1 yard is equal to 3 feet, 1 yard is equal to 36 inches, 1 mile is equal to 5 to 80 feet. Okay, so for this table naman, so you have to memorize that 1 inch is equal to 2.54 centimeter, 1 meter is equal to 3.28 feet. 1 mile is equal to 1.61 kilometer. Okay, so for the second table, it's actually more advisable and easier if we use this conversion line instead of memorizing this conversion factors. Okay, so it's much easier, okay, than memorizing this. Okay, so how to use this? So let's say we're going to convert meter to millimeter. Let's say 1 meter, convert that to millimeter. So what we're going to do is just count, okay, the move, okay, from meter to millimeter. Okay, so we're just going to count that from meter to millimeter. So that will be 1, 2, 3. So that will be the number of move Okay, from 1, okay, so from 1, we're going to move 1, 2, 3. So 1, so that will be 1, 2, 3. So we're going to add 3 zeros. Okay, so let's say that 1 meter, it's actually equivalent to 1 with 3 zeros at the right, so that will be 1,000. So 1 meter is equal to 1,000 millimeter. Now for, let's say, meter to kilometer, we want to convert that. Okay, so the movement here will be from right to left, right? So if we're going to convert meter to kilometer, that will be from right to left. Okay, so what we're going to do here is count the number of moves from meter to kilometer. So that will be 1, 2, 3. But here, if we're going to convert it um, with the direction to the left, okay, so what will happen here, the 1, okay, will be included in the count of your move. So let's say 1, okay, 1 meter to kilometer. So you will include that. So this will be 1, 2, 3 moves, but you will include 1 in your move from right to left. So that will be 1, 2, 3. So what will happen is that you're going to add 2 0. So that will be 0.001 kilometer. So 1 meter is 0.001 kilometer. Now, let's say we want to convert meter to centimeter. So 1 meter, so the direction is from left to right. So you will just count the move from meter to centimeter. That will be 1, 2. So you will just add 2 zeros. That will be 100 centimeter. 1 meter is equal to 100 centimeter. Okay, so that is also the same for meter to decimeter. So that will just be 10 decimeter. 1 meter is equal to 10 decimeter. Now, if we want to convert, let's say, decameter to meter, so from left to right pa din yan. So that will be 1 decameter. And then 1 movement to the right. So that will be 1 0. So 1 decameter is 10 meters. Okay, 1 hectometer will be 100 meters. And 1 kilometer is 1,000 meters. But now, if you're going to convert meter, let's say, to hectometer, so the movement will be 1, 2. But you will include 1 in your count. So from 1, so that will be 1, 2. So it will have 0 or 1 0. That will be 0.01. So 1 meter is equal to 0.01 hectometer. Now for decameter, so that will have 1 movement. So that will be 1 meter is equal to uh, how many move? There's only 1 move, no? So 1 meter. From 1, you will count from right to left, so that will be 1. So that will just be 0.1. So 1 meter is equal to zero point 0.1 decameters. Okay. Now, for weight, okay, you have to memorize that 1 pound is equal to 16 ounces, 1 ton is equal to 2,000 pounds, and 1 slug is equal to 32.174 pound. Okay, now for the third table for weight or mass, so 1 ounce equal to 28.3 grams, 1 pound is equal to 0.45 kilogram, 1 slug is equal to 14.59 kilogram. Also for force, okay, so 1 pound is equal to 4.448 newton, and 1 newton is equal to 10 raised to the fifth dynes. Also, if you're going to use a conversion line, no, so this is also applicable for other suffixes. Let's say it's not just applicable for meters, it's also applicable for liter, for grams. Okay, so what will only change here is the suffix, but the prefixes kilo, hecto, deca, okay, deci, centi, milli, it will be the same. So we can also use uh, kilogram, okay, hectogram, decagram, okay, so also for liter, it can be applied. Now, let's talk about the prefixes that we will frequently use also here in this course. So you have to be familiar with tera, giga, mega, kilo, hecto, deca, deci, centi, milli, micro, nano, and pico. Okay, so let's say you want to convert, let's say terameter. Okay, terameter to meter. So if you convert that, that will just be 1 tera. It will be equal to 1 raised to 12. Okay, so that will be 1 with 12 zeros at the right meter. Okay, so that's how you convert that. For giga, okay, let's say 1 gigameter, that is equal to 1 with 9 zeros to the right meter. Okay, for mega, that will have 6 zeros. For kilo, 3 zeros. Hecto, 2 zeros. Deca, 1 zero. For deci, so what will happen here, let's say 1 meter, so that will be 0.1 decimeter. Okay, 1 meter, that will be 0.01 centimeter. 1 meter, that will be 0.001 millimeter. Okay, and so on for this. No? So you have to be familiar with these prefixes. Okay, so let's take this examples. Okay, so we have to convert the following. The first one is from 450 kilometer to centimeter. The second one is from 5 meters to inches. The third one is 400.35 hectogram to slug. And then 60 miles per hour to meter per second. And one slug feet per second squared to kilogram meter per second squared. So let's start answering these examples. So for the first one, okay, so this is 450 kilometer to centimeter. So as I've mentioned earlier, okay, in conversion of units, it's much easier if we use this conversion line. Okay, so if we're going to convert kilometer to centimeter, since the direction is from left to right, so we're just going to count the move from kilometer to centimeter. So that will be 1, 2, 3, 4, 5. Okay, so basically, we know that 1 kilometer is 1, tapos with 5 zero, so that will be 100,000 centimeter. Okay, but if we're going to solve this, okay, using solution, okay, so let's say 450 kilometer and you want to convert that to centimeter, you just multiply it with its conversion factor. Okay, so with this fraction, wherein the denominator will be the unit, okay, that you want to be canceled. Okay, so let's say kilometer to centimeter. So what you're going to put here in the denominator will be the unit that you want to cancel, which is kilometer. So for every 1 kilometer, that is 100,000 centimeter. Okay, so if you're going to compute this will be ilang zero ba to? This will be 45 million centimeter. So for every 450 kilometer, we have 45 million centimeter. Okay, so that's the first example. The second example, from meters to inches. Okay, so in your conversion factors, okay, in the table, okay, we don't actually have a direct conversion from meter to inches, right? What we have here is from meter to feet, okay, from inches to centimeters. So you have a choice, okay, for this problem. So you can convert, okay, first this unit, okay, to the unit, okay, that has conversion with inches. Okay, let's say from meter, you can convert that to feet. Okay, wherein you know that for every 1 feet, there is 12 inches, right? So you can use that. But you can also do that. You convert meter to centimeter, and then from centimeter, okay, you convert that to inch. So we already have conversion factor from centimeter to inches, so we can use that. So let's do this. So this will be the solution. So for 5 meters, okay, to inches, let's first convert this to centimeter. Okay, so for every 1 meter, there is 100 centimeters. So you're going to put meter here in the denominator to cancel this. Okay, to cancel that. Okay. Now, for centimeter, you still have to convert this to inches. So we know that we have this conversion factor from inch to centimeter. So for every 1 inch, there is 2.54 centimeters. So what you're going to put here in the denominator is the unit that you want to cancel, which is centimeter. Okay, so 2.54 centimeter, that is equal to 1 inch. So centimeter will be canceled. Okay, and then computing this, so this will give you 196.85 inches. So that will be the answer. So let's proceed now to the third example. So this will be from hectogram to slug. So as you can see in the table, okay, so we don't have a direct conversion from hectogram to slug, but we have here slug to kilogram. So what we can do here is convert first hectogram to kilogram, okay, so that we can use this conversion. Okay, so let's convert hectogram to kilogram. So we can actually use the conversion, this conversion line. Okay, so let's say kilogram and hectogram. So for every 1 kilogram, we have that will be 10 hectogram, right? But we can also use, let's say 1 hectogram, that is also equal to 0.1 kilogram, right? So either of those two conversions we can use for this. Okay, so this will be the solution. Okay, so 400.35 times the conversion factor, wherein what you're going to put in the denominator will be the unit that you want to cancel, which is hectogram. So for every 10 hectogram, we have 1 kilogram. So hectogram will be canceled. And then for kilogram, okay, so from kilogram, we have to convert that to slug. And we have here a conversion factor, okay, that 1 slug is equal to 14.59 kilograms. So what we're going to put here in the denominator will be the unit that we want to cancel, which is kilogram. So for every 14.59 kilogram, we have excuse me, 1 slug. So we cancel that kilogram and it's now in slug. Okay, so computing this will give you 2.74 slug. So that will be the answer. Now, for the fourth example, this is from 60 miles per hour to meter per second. Okay, so if we're going to convert this, we're going to convert mile to meter and then hour to second. Okay, so from mile to meter, again, we don't have a direct conversion from mile to meter, but we have from mile to kilometer. So what we're going to do here is convert first the mile to kilometer, and then from kilometer we convert it to meter. So for every 1 mile we have 1.61 kilometers, so miles will be canceled here. Okay, so from kilometer you can now convert that to meter. So for every 1 kilometer we have 1,000 meter, so it will be canceled. Okay, now it's okay now for miles to meter, no? So let's proceed now to r to second. Okay, so we're going to convert r to second. So r is in the denominator. So what we're going to do here, we have to put hour in the top, okay, of your conversion fraction. Okay, so for every 1 hour, we know that for every 1 hour, we have 60 minutes. So we put r here to cancel this. Okay, so for every 1 hour, there is 60 minutes. Okay, but we need to convert that still to seconds. So for every 1 minute, okay, there is 60 second. Okay, so this will be canceled. Minutes will be canceled. So computing this will give you 26.83 meter per second. So this is the equivalent of 60 miles per hour. It is 26.83 meter per second. So that will be the answer. Okay, for the last example, this is from 1 slug feet per second squared to kilogram meter per second squared. So this is actually the unit for force, right? So slug feet per second squared is a pound, and kilogram meter per second squared is actually Newton, no? So we actually know that for every 1 pound, there is 4.448 Newton. So we're going to confirm that if that is true. Okay, so let's convert this unit to this unit. Okay, so for our solution, okay, we have to convert slug to kilogram and then feet to meter. Okay, so converting slug to kilogram, okay, using this formula, okay, for this solution. Okay, so we know that for every one slug, okay, we put slug at the denominator to cancel slug, ha? Okay, for every one slug, we know that we have 14.59 kilograms. So slug will be canceled, okay? And then now we have to convert feet to meter. So we know that for every 3.28 feet, there is 1 meter. So we put feet here in the denominator to cancel feet. So that will be 1 meter over 3.28 feet. So it's already okay, no? Since we converted already slug to kilogram and feet to meter. So second squared will be the same. Okay, will just be the same. So computing this, so slug will be cancelled, feet will be cancelled. So what will remain is kilogram meter per second squared. So this is 4.448 kilogram times meter per second squared. So this is correct, right? So this is the conversion that we use. That for every 1 pound, there is 4.448 Newton. So for problem formulation and the accuracy of solution, so this will be an important tip, okay, on how you are going to approach, okay, all the problems that we're going to solve for this course, okay. So to help you develop an engineering approach to problem analysis, you will find it instructive to divide your solution for each homework problem into the following parts. So the first one is given. Okay, so after carefully reading the problem statement, list all the data provided. If a figure is required, sketch it neatly and approximately to scale. Okay, so the second one is find. So state precisely the information that is to be determined. So the third one is the solution. So solve the problem, showing all the steps that you use in the analysis. Work neatly so that your work can easily be followed by others. Okay, and the fourth one is to validate. So many times, an invalid solution can be uncovered by simply asking yourself, does the answer make sense? So the answer should be logical. So you have, after you solve every problem, you have to check your solution and your final answer if the answer, okay, is logical. If it's not logical, you have to go back where you have gone wrong, okay, in your solution. So now let me introduce to you the resultant of force system. So this topic will actually be discussed on our next discussion, but I will introduce to you now the definition of resultant. So resultant is a single force or vector that is the equivalent of a set of forces or vectors. Okay, so let's say we have here this force system. Okay, so we have two forces here, and these two forces can actually be represented by a single force, which is the resultant. So let's say um, this force is 30 Newton. It is directed to the left, and this force directed to the right is 100 Newton. So if we're going to get its resultant, it will just be 70 Newton directed to the right. So this 70 Newton, okay, force directed to the right, it can represent these two forces. Okay, and also for the following force system, so this is a concurrent force system, non-concurrent force system, and parallel force system. So they can all be represented by a single force. So for this concurrent force system has four forces, right? So these four forces, okay, the ones in the blue ink, okay, so these four forces are actually the component forces which make up the resultant. So these four forces can be represented by this single force called resultant, which is in the red ink. So the direction and the magnitude of the resultant, okay, will be dependent on the direction and magnitude of most of the forces. Okay, so if most of the forces in this force system are directed to the right, let's say to the right, so obviously your resultant will also be directed to the right. Okay, so if your um, forces in this force system, okay, most of them are directed to or upward, directed upward. So obviously, the direction of the resultant will also be directed upward, but it still depends on the magnitude, no? So on our next discussion, we will talk about compute, okay, resultants for this type of force system. Also for non-concurrent force system, okay, so these forces in blue ink, okay, so it can be represented by a single force. So this is the resultant for this force system. And also for parallel force system, it can be represented by a single force. Okay, so this force system can be represented by its resultant. So that is the force that is in red ink, no? So that will be the resultant. So that concludes this session. I hope you learned. So see to it that you have learned the intended learning outcomes for this topic. And also don't forget to answer the assessment task in the latter part of the course material uploaded. So study well, keep safe, and God bless.